Okay, we have what at first look seems to be a very simple problem. Two opposite charges are located 12 centimeters apart as shown. So we can see in the figure above we have a positive 20 millicoulomb charge. Milli means 10 to the minus 3. So there's 20 millicoulombs here. And then 12 centimeters away from that first charge is a second minus 30 millicoulomb charge. And we can see that these are separated 12 centimeters apart. Now we can go ahead and label these if we want. We can call the leftmost charge Q1 and the rightmost charge Q2, and we can imagine ourselves having a little coordinate system, say X, Y, with the origin at the leftmost charge. Of course, we could put our coordinate system anywhere, but when we can, we always like to put our coordinate system where something is going to go to 0, and in that case, that would be the position of this 20 millicoulomb charge. Now the problem asks, where can a third charge of 4 microcoulombs be placed so that it feels no force? So what does that mean? It feels no force. Well, obviously, each of these charges is going to apply a force on our 4 microcoulomb charge. But if the charge is placed in just the right spot, the force from the leftmost charge Q1 and the force from the rightmost charge Q2 will balance. And so that's what we want to do. We want to find the force, or I'm sorry, we want to find the position where the forces from these two charges will balance. So I can place my 4 microcoulomb charge at that position and it will feel no net force. And this problem, if we were being really careful in the way we were describing it, we would say no net force, because that's really what we mean. Okay, so what we want to do is we want to find a possible location where the force from this leftmost charge can balance the force from this rightmost charge. Now, if we write down the formula for the force acting on a charge in an electric field, we know that F is equal to Q times E, and F and E are both vectors. Where will the force be 0? The force is going to be 0 where the electric field is 0. So what we really want to do is we want to calculate where is the electric field from these two charges going to add together and give you 0. So this is what we're looking for. We're looking for the place where E equals to 0. Now this problem is often framed lots of different ways. Where is the electric field 0? You could simply ask that. The way this problem is framed was, where will a charge be able to be placed so that it feels no force? Again, that means the same thing. It's basically, where is the electric field 0? And so we've got these two charges and we want to calculate where the electric field can be 0. Hopefully it's clear just from the picture that the only possible place where the charges could have forces that cancel would be somewhere along the line joining the two charges. It has to be on that line somewhere, because if I were to pick a point in space right there, if you simply draw the electric field vectors from the positive charge and the negative charge at that point in space, you'll see they don't line up. There's no way that they could cancel one another. But if I pick a point along this line, there is a possibility that the charges could in fact cancel. The question is, where do I put that point? Now there's 3 possibilities. There's a possibility that I could put the charge to the left, or in between, or to the right. And so what we want to do is we want to determine which of these 3 possibilities is true. Will the place where the fields from the charge go to 0 be to the left, in between the two charges, or to the right? And of course, they have to be on that line joining the two charges. So let's consider those 3 cases. Now, first of all, let's consider the position on the right over here. Is there a possibility that those electric fields could cancel? Now, let's remind ourselves what the formula for the electric field from a point charge is. We know that E is going to have a magnitude of KQ over R squared. That is the magnitude of the electric field due to a point charge. Now, K is of course a constant, So the two variables that come to play are going to be the magnitude of the charge and the distance between the charge and the point in space that we're interested in, represented by our little blue x's. So let's consider the region to the right. Is it possible for the charges to cancel there? Well, if we draw the electric field, remembering that this is Q1 and this is Q2, so let's consider the region to the right of the two charges. This position over here. Is it possible for the electric fields in that position to cancel? So if I consider the electric field from Q1, it's going to be pointing to the right because Q1 is positive, and a positive test charge placed here is going to feel a force to the right. Now if I consider the electric field from Q2, it's going to be to the left because Q2 is negative and a little positive charge there is going to be going in that direction. So it looks at first look like these two electric fields, this would be E1 and this would be E2. It looks like they could possibly cancel, but if you look at it closer, you'll see that they can't. And this is really the hardest part to understand. Why can't E1 and E2 cancel? And it has to do with this formula here. And so the way to think about it is this. If I look at this formula, E is equal to KQ over R squared. What makes E bigger? What makes E bigger is having a bigger Q. So everything else being the same, if Q is bigger, you're going to have a bigger electric field. On the other hand, what makes E bigger is having a smaller R because you're dividing by a smaller number. If I divide by a half, then that makes this bigger. So as R gets smaller, you get a bigger E. And so let's compare E1 to E2 because clearly the charge here is bigger from E2. And so E2 is going to be bigger because the charge is bigger. Also, the distance is smaller. The distance from charge 2 is smaller than the distance from charge 1. So that means that E2 is going to be bigger because it has a bigger charge, and it's going to be bigger because it has a smaller distance. E2 is always going to be bigger than E1. That means it can't possibly cancel there. And so that eliminates any position to the right of the two charges as a possible location where the two fields could cancel. Now let's consider a position in the middle. We have the negative charge on the left is going to have an electric field that is going to the right. That would be E2. And the positive charge is also going to have an electric field going to the right. That would be E1. Both of those electric fields are going to the right. And remember, we determine that direction by imagining a little positive charge at a position of interest. And so the positive charge here is going to be attracted to the negative charge. That means E2 is going to be to the right. It's going to be repelled by the positive charge. That means E1 is going to be to the right. And so both of these electric fields are pointing to the right. They can't possibly cancel. Now, by process of elimination, since the other two places don't work, I think you're probably going to guess that it's going to work over on the left. But let's see how it could be possible. The charge here is smaller. So that means that the electric field from Q1 is going to be smaller because of the size of the charge. But the distance to Q1 is also smaller, and so that means the electric field from Q1 is going to be bigger because of the distance. And so here, if I look at my formula again, I have these things are not working in the same direction. In other words, they're not both acting to make E bigger. One of them is acting to make E bigger, the other one is acting to make E smaller. And you can see the same thing with charge 2. The distance is bigger, but the charge is bigger. And so these guys are canceling each other out. And so there has to be some position over here where there is a balance. So as a rule, when you want to work a problem like this, the first thing to do is figure out where on the line the electric fields could possibly cancel. Because again, our goal is to figure out where the electric field is equal to zero. And so we know that it can't possibly cancel in the middle. It can't possibly cancel to the right. It could possibly cancel to the left. So we just have to find the location where that is possible. Now we're going to set this up. I'm going to redraw this system real quick. We have a positive charge here. We have a negative charge here, and we have some distance between them. In our case, the distance is 12 centimeters, but it could be any distance, so you just plug in the distance into your problem. And you're going to see in a minute, it doesn't actually matter what the units are, whether you have millicoulombs or microcoulombs or coulombs, whether you have centimeters or meters. You don't have to do any converting. I probably will when I do the calculation, but you'll see that you don't actually have to do that. But let me do the calculation. You'll see what I mean by that. But for now, we need to figure out where over here the charges could balance. And so I'm going to say that that's some distance x from the leftmost charge. Now, when we plug these values into R to calculate the magnitudes of the electric field from this point, from the positive charge, Q1, that's just going to be x. The electric field from the negative charge is going to be this whole distance, which would be x plus d. And so if you can see that the whole distance from here to there is d, from there to there is x, so the whole entire distance would be d plus x or x plus d. And so when we plug these in, those are the values for the R that we're going to use in our formula. So let's do that. All right, so I have my two charges, my positive 20 millicoulomb charge and my negative 30 millicoulomb charge. And I have my point P, which is some distance x away from the leftmost charge. And I want to calculate the electric field at P. Now, if I look at my point P here, I'm going to look at the charge from this positive charge. The electric field there is going to be to the left. And so if I draw the electric field at my point P, I can see that E1 is going to be to the left, and then E2 is going to be to the right. Again, if I'm thinking about this being a positive charge here, it's going to be repelled by the leftmost charge, Q1, and so E1 is going to be to the left. It's going to be attracted to the negative charge, Q2, and so E2 is going to be to the right. What's true when those two electric fields balance? When those electric fields balance, their magnitudes are equal. And so what I'm going to do is I'm going to write this all out. I'm going to set E1 equal to E2 and solve for x. So E1 magnitude is equal to K Q1 over R1 squared. And E2 is equal to K Q2 over R2 squared. And so we can just plug in those values now. But before I do that, I can immediately see that the K's are going to cancel. That makes my life a little bit easier. And so I can now just plug in what I know. So Q1 is 20 microcoulombs. And by the way, this whole thing on the right is equal to E2. But we know that E1 and E2 have to equal each other at the point P that we're interested in. And this guy is E1, this guy is E2, and they're equal to each other. And so I can now plug in values. I can plug in values for Q1 and R1, and what I'll find is that I get 20 times 10 to the minus 3 coulombs divided by x squared. That's E1. And how do I know that? Because x is the distance, and so you're dividing by the distance squared. Q, 20 plus 20 millicoulombs is the charge. And so that's 20 times 10 to the, and oops, that should be minus 3. Thank you. Now that is going to be equal to E2, which is Q2, 30 millicoulombs, 30 times 10 to the minus 3 coulombs. divided by the whole distance, x plus 12, all squared. And so I've got this whole guy here is E1, and this whole guy here is E2. Now, why didn't I put in minus 30 for that minus 30 millicoulombs? Because what we're looking at here is magnitudes. It's the magnitudes that are equal when they balance. And so we already have the direction from the picture. We don't need to include the minus signs. We're just looking at the magnitudes. And we're saying that when these two vectors are in balance, they are oppositely directed, but equal in magnitude. And so these are the magnitudes, and we've just plugged in the numbers. So now all we have to do is solve for x. Now, before we solve for x, there is one other thing that I can note. I can kill that 10 to the minus 3 coulombs because they cancel. And I can also kill a factor of 10 here. I can divide both by a factor of 10, and I'm left with 2 over x squared equals 3 over x plus 12 quantity squared. And I just want to solve that for x. And so we'll look at how to do that on the next slide. Okay, so this is what we had from the previous slide. We have 2 over x squared equals 3 over x plus 12, all quantity squared. And the way that we can solve this, there are actually a couple of different ways. The quick way that's probably obvious is just to cross multiply. And so if I cross multiply, I get 2 times x plus 12 squared is equal to 3x squared. So I can say 3x squared, that's multiplying these guys together, is equal to 2 times x plus 12 centimeters squared. And then what I'll do is I will just FOIL this guy out, and I get 3x squared is equal to 2 times x squared plus 24x plus 144. And I'm being a little bit sloppy with my units there, but we're just trying to solve for the quadratic equation. And of course, I can distribute this 2, and I get that 3x squared is equal to 2x squared plus 48x plus 288. And we want to solve that for x. So we bring everything over to one side, and 2 comes over, subtracted from the 3 makes us just 1x squared minus 48x minus 288 is equal to 0. And of course, that's just a quadratic equation which we can solve with the quadratic formula. Minus b plus or minus the square root of b squared minus 4ac all over 2a. And if I plug those values in, I get positive 48 plus or minus the square root of 48 squared minus 4 times 1 times 288. And that's minus 288, so the minus and a minus makes a plus, and all that is divided by 2. And when I plug all of that into the quadratic formula, I get two solutions, which are x is equal to 53.4 centimeters, or x is equal to minus 5.4 centimeters. And which one do I pick? Well, we're solving for a distance, and distances can't be negative, and so we're going to pick the positive value, and that's going to be 53.4 centimeters. And that is the distance away from the leftmost charge where the two electric fields will balance. I can place a third charge there. Since there's no electric field from the other two charges, that charge will not feel a force. And it doesn't actually matter how big the third charge is, because the electric field at that position is 0. No other charge placed there is going to feel a force. Okay, so we have the same problem here, But what's changed is the negative 30 charge is now positive 30. And so what's different if both of the charges are positive or negative? It doesn't really matter. In the previous problem, you had one positive charge and one negative charge. In this problem, you have two positive charges. And what's different is that out here, both electric fields are going to be repulsive. E1 and E2 are both going to be to the right, and so they can't possibly cancel. To the left, both electric fields are going to be repulsive, so they can't cancel. But at some position in the middle, the electric field from the leftmost charge is going to be like that. The electric field from the rightmost charge is going to be like that. And there's a possibility that they could cancel. So how do you set the problem up if the two charges are the same type, if they're both positive or they're both negative? And so what we do is we have this positive charge here and this positive charge here, and we know that there's some distance d between them. In this case, it's 12 centimeters, but it could be any distance, whatever it is. We know that the location is going to be at some point between the charges. And so if this distance here is x, we can now calculate, let's say, we'll call this Q1 again and this Q2 again. We can say that E1 magnitude is going to be k Q1 over x squared, and that's going to be equal to E2 magnitude, which is equal to k Q2 over, now here's the distance between the point and the charge. That distance is d minus x. And if you can see that, if this whole thing is d, I'm subtracting out the x, I'm left with d minus x. And so instead of, in the previous example, we had d plus x squared, here we have d minus x squared. But again, at that point, the problem is set up, and it's just algebra. You cross multiply, you do the quadratic formula, and you take the positive root, and that'll be your solution for the x position where they balance. And that's how you work these kinds of problems.